Have you ever wondered why the periodic table is called the heart of chemistry? Every reaction you study, every element you encounter, every equation you balance begins right here with this masterpiece of science. Welcome to the Mother of the Periodic Tables, Part 1, a special journey designed to unlock the very foundation of chemistry and make you see the periodic table like never before. In this series, we're going beyond memorization. We'll explore the secrets behind atomic arrangement, periodic trends, and the hidden logic that makes chemistry predictable, and yes, even fun. Whether you're preparing for your KCSE exams or just want to finally make sense of those mysterious groups and periods, this is your moment. From A to Z, every question in this series will challenge your mind, sharpen your understanding, and help you grasp chemistry concepts with confidence. So grab your notebook, focus your mind, and let's dive into the table that rules them all, the mother of the periodic tables. Because once you understand this, you understand chemistry itself. Now let's dive into question A. And this one's a real mind opener. The question asks, to which group of the periodic table do the following elements belong? But before we rush to answer, let's pause for a moment. So what exactly is a group? A group is a vertical column in the periodic table. Each group contains elements that share the same number of electrons in their outermost energy level, which gives them similar chemical properties. To assign a group to any element, simply look at its number of outermost electrons. We call them valence electrons. If you know how to write the electron configuration of an element, then it becomes easier. For instance, V has the electron configuration of 2,6 with 6 electrons in the outermost energy level. Therefore, V is in group 6. L has electron configuration of 2,1 with 1 valence electron, hence belongs to group 1. R with electron configuration of 2,8,3 has 3 valence electrons. For this case, belongs to group 3. All right, let's move on to question B. And this one's another key to unlocking the periodic table puzzle. The question says, state 2 elements that belong to period 4. But before we name them, let's first understand, what's a period? While groups stand tall like pillars, periods stretch across the table horizontally from left to right. Each period represents elements that have the same number of occupied energy levels. So, when we talk about period 4, we're referring to all the elements whose atoms have 4 occupied energy levels. It's like moving across a street of houses. Each house or element has a different design, but they all share the same number of floors. For this case, the elements in period 4 include N and Q, even Y and X. Now let's tackle question C, which asks, to which periods do the following elements belong? Here's where many students often get stuck, but there's a quick and clever way to crack it. The secret lies in the electron configuration of each element. Element T has electron configuration of 2,6. The 2 electrons occupy the first energy level, while the 6 electrons occupy the second energy levels, meaning element T has 2 occupied energy levels, and therefore belongs to period 2. Element U belongs to period 3 since it has 3 occupied energy levels, because it has the electron configuration of 2,8,5. Let's now move to question D, and this one introduces something exciting. The chemical families of the periodic table. The question asks, state the chemical family into which the following elements belong. Now, before we match the elements to their families, it's important to know what we mean by a chemical family. A chemical family is simply a group of elements that share similar chemical properties because their atoms have the same number of valence electrons. Think of it as a big family where all the members behave almost alike. In our syllabus, we focus on 4 major families. Alkali metals, found in group Y, these are the super reactive metals like sodium and potassium. They react quickly with water and form strong bases, or alkalis. Alkaline earth metals, that's group 2. They're slightly less reactive, but still form basic compounds, like calcium and magnesium. Halogens, these live in group 7 and include chlorine, fluorine, and iodine. They're colorful, reactive nonmetals that love to form salts. Noble gases, found in group 8, these are the unreactive gases, like neon, argon, and helium. We also briefly mentioned the transition elements, which include metals known for forming colored compounds and also have variable oxidation states. So when identifying a chemical family, always check its group position and reactivity pattern. That's how you'll instantly know which family your element belongs to. Therefore, for this case, elements P and Q belongs to the alkaline earth metals family, W and X belongs to the halogen family, Z belongs to the noble gases family, Y is a transition element, L, M, N, and O belongs to alkali metals family. Let's now turn to question E, which says, elements L, M, N, and O belong to the alkali metals family. Explain why they are referred to as alkali metals. Now, this is a question that goes straight to the heart of chemical behavior. The term alkali comes from an Arabic word meaning ashes of plants, and it's not just a fancy name. These metals earn the title alkali metals because of what happens when they meet water. Each of these elements, like sodium, potassium, and lithium, reacts vigorously with water to form alkaline solutions, or bases, such as sodium hydroxide, NaOH, and potassium hydroxide, KOH. During this reaction, they also release hydrogen gas, often with hissing sound, heat, or even a tiny explosion, a classic chemistry demonstration. So in short, they're called alkali metals because they are metals that produce alkalis when they react with water. Now, the next part of the question asks something quite interesting. Give a reason why element K does not belong to this chemical family, the alkali metals. And here's the twist. Element K is hydrogen. At first glance, hydrogen seems to fit right in with the alkali metals family. After all, it's in group 1 and has one valence electron, just like them. But in chemistry, appearances can be deceiving. Hydrogen is not a metal. It's a non-metallic gas. Unlike the alkali metals, it doesn't form metallic bonds or shiny solids, and it doesn't react with water to form an alkali. So while hydrogen shares a similar outer electron pattern, its chemical and physical behavior is completely different. That's why it doesn't truly belong to the alkali metals family.
Let's now move to question F, which takes us deeper into one of the most important ideas in chemistry, ion formation. The question says, write the electron configuration of the ions of element P and U and the atom of R. Here, element P is magnesium, element U is chlorine, and element R is aluminium. Before we write their configurations, let's recall a key principle. Atoms form ions to achieve a stable electron arrangement, usually the same as that of a noble gas. Now, let's start with magnesium, P. Its atomic number is 12, so its neutral atom has the configuration 282. To become stable, magnesium loses 2 electrons from the outermost energy level, forming Mg2+. The ion's configuration then becomes 28. Next is chlorine, Yo, with atomic number 17. The neutral atom's configuration is 287. Chlorine gains 1 electron to complete its outer shell, forming chloride ion with the configuration 288. Lastly, aluminium, R, atomic number 13. Its neutral atom has electron configuration of 283. Now let's look at question G, which asks us to draw the structure of the ion of element L. And in the above periodic table, L represents lithium. Here's the structure I've drawn using dots and crosses to show how the electrons are arranged. In its neutral state, lithium has 3 electrons, 2 in the first energy level and 1 in the second. But when lithium forms an ion, it loses that 1 outer electron to achieve a stable electron arrangement, leaving it with 2 electrons. Just like helium, a noble gas. This loss of 1 electron gives lithium a positive charge, forming Li+. So, in the dot and cross diagram, you'll notice that I haven't drawn the outer shell since it's now empty, and the ion is surrounded by square brackets with a small plus sign on the upper right, indicating it's a positively charged ion. This simple structure clearly shows how metals form positive ions, cations, by losing electrons to gain stability, a fundamental rule in chemistry. Now let's move to the next part of question G, which asks us to draw the structure of the ion of element U, and element U is phosphorus. Here's the dot and cross diagram I've drawn to represent the ion. Phosphorus is a nonmetal found in group 5, meaning it has 5 valence electrons in its outermost shell. To achieve a stable octet, that is, 8 electrons in the outer shell, phosphorus needs to gain 3 electrons. When it does, it forms the phosphide ion, written as P3-. In the dot and cross structure, you'll notice that the phosphorus atom is surrounded by 8 electrons. The original 5 it had, plus the 3 gained. I have indicated them with 3 crosses, from a metal during bonding. The entire ion is then enclosed in square brackets, with a small 3- charge at the upper right corner to show that it's now a negatively charged ion, also called an anion. This clearly demonstrates how nonmetals form negative ions by gaining electrons, the exact opposite of what metals like lithium do. Now let's look at question H, which asks, write the formula of the most stable ion of element R. In this question, element R represents aluminium. Aluminium is a metal found in group 3 of the periodic table, meaning it has 3 valence electrons in its outermost shell. To become stable, aluminium loses all 3 of these outer electrons, forming a positively charged ion known as the aluminium ion. When it loses those 3 electrons, its electron arrangement becomes the same as that of neon, a noble gas, which is completely stable. Therefore, the formula of its most stable ion is Al3+, or R3+. Now let's talk about element 5, which represents oxygen. Oxygen is a nonmetal found in group 6 of the periodic table. That means it has 6 valence electrons in its outermost shell, just too short of a full, stable octet. To become stable, oxygen gains 2 electrons from a metal during bonding. By doing so, it achieves a full outer shell of 8 electrons, the same configuration as neon, a noble gas. When oxygen gains these 2 electrons, it forms the oxide ion, written as O2-. The 2 to the negative charge shows that oxygen has gained 2 electrons, making it a negatively charged ion, or what we call an anion. So, the formula of its most stable ion is O2-, or V2- for this case. Now we come to question 1, and this one ties together everything we've learned about ions and their charges. The question asks us to select the elements that form ions with charges of +1, +2, +3, -1, -2, and -3. Let's decode this step by step. In the periodic table, the group number of an element often reveals the charge of its ion. Metals on the left side of the table tend to lose electrons, forming positive ions, cations, while nonmetals on the right side tend to gain electrons, forming negative ions, anions. Let's begin. Group 1 elements, K, L, M, N, and O, each have 1 valence electron. They lose 1 electron to become +1 ions, also called monovalent cations. Group 2 elements, P and Q, have 2 valence electrons. They lose both to form +2 ions, or divalent cations. Group 3 element, R, has 3 valence electrons, so it loses 3 to form a +3 ion, known as a trivalent cation. Now to the nonmetals group. 7 elements, W and X, have 7 valence electrons. They gain 1 electron to complete their outer shell, forming -1 ions, or monovalent anions. Group 6 element, V, has 6 valence electrons. It gains 2 electrons, forming a -2 ion or divalent anion. Group 5 element, U, has 5 valence electrons. It gains 3 electrons to complete the octet, forming a -3 ion, or trivalent anion. And there you have it, a perfect pattern. Metals lose electrons to form positive ions, while nonmetals gain electrons to form negative ions. all following their group positions. If you can remember this trend, you've mastered one of the biggest keys to understanding how elements bond and form compounds in chemistry. Now, let's look at question J, which says, the atomic mass of element U is 31. Draw the atomic structure of element U, showing the composition of the nucleus and the distribution of electrons in the energy levels. Here, element U represents phosphorus. Phosphorus has an atomic number of 15, meaning it contains 15 protons in its nucleus. Since it's a neutral atom, it also has 15 electrons arranged around the nucleus. The atomic mass is 31, so to find the number of neutrons, we subtract the atomic number from the mass number. 31 minus 15 equals 16 neutrons. That means the nucleus of a phosphorus atom contains 15 protons and 16 neutrons, tightly packed at the center. Surrounding this nucleus are 3 energy levels where the 15 electrons are distributed as follows. First shell, 2 electrons. Second shell, 8 electrons. Third shell, 5 electrons. This gives a complete electron arrangement of 2, 8, 5, which matches phosphorus's position in period 3, group 5 of the periodic table. So, in the atomic structure, you see the nucleus with 15 protons and 16 neutrons, and 3 energy levels with electrons neatly arranged 2, 8, and 5. This clear structure helps us understand why phosphorus behaves the way it does. It has 5 valence electrons, ready to gain 3 more to reach a stable octet. The question K says, element G is in the second period of the periodic table and forms G3- ions. Indicate the position of element G on the grid above. From the information given, we know that element G forms a 3- ion, meaning it gains 3 electrons when forming an ion. This behavior is typical of nonmetals in group 5, such as nitrogen or phosphorus, which need 3 electrons to complete their outer shell. Since element G is in the second period, it must be found in the second row of the periodic table. That is, among elements whose outer electrons occupy the second energy level. The only element in period 2, group 5, that forms a 3- ion is nitrogen, N. Therefore, on the grid, element G should be placed in the second period and group 5 column, representing nitrogen. Question L. Write the formula of the compound formed when the following elements react. A, P, and V. To write a chemical formula, we first determine the valency of each element. P is magnesium, and it has a valency of 2, because it is in group 2 and loses 2 electrons to form Mg2+. V is oxygen, and it has a valency of 2, because it is in group 6 and gains 2 electrons to form O2-. Now, to write the formula, we cross over the valencies so that they balance. Valency of magnesium is 2. Valency of oxygen is 2. When we cross them over, they reduce to a 1-to-1 ratio, since 2 and 2 simplify. So, the formula is MgO. Each magnesium atom combines with 1 oxygen atom to satisfy both valencies. B, R, and E are aluminium and chlorine, respectively. Next, we find the valencies. R is aluminium, and it has a valency of 3, as it is in group 3 and forms Al3+ ions. E is chlorine and has a valency of 1, as it is in group 7 and forms Cl- ions. Now cross over the valencies. Valency of aluminium is 3. Valency of chlorine is 1. When we cross them over, the valency of aluminium, 3, becomes the number of chlorine atoms, and the valency of chlorine 1 becomes the number of aluminium atoms. So the formula becomes AlCl3. 1 aluminium atom combines with 3 chlorine atoms to balance their valencies and form a stable compound. Question M. Let's now look at compounds formed between elements and common radicals, such as nitrate, NO3-, sulfate, SO42-, and carbonate, CO3 2-. Remember, a radical is a group of atoms that behaves as a single ion. It carries an overall charge just like a simple ion. We'll use the valency crossover method to write the correct chemical formulae. Now, the nitrate of Q. Q is calcium, and it has a valency of 2. It forms Ca2 plus ions. The nitrate radical, NO3, has a valency of 1. It forms NO3 minus ions. Now, cross over the valencies. Valency of calcium is 2. Valency of nitrate is 1. So, 2 nitrate ions are needed to balance 1 calcium ion. The formula is thus Ca, open the bracket, NO, 3, close the bracket, 2. The brackets around NO3 show that the whole nitrate group is multiplied by 2. Next, the sulfate of RR is aluminium with a valency of 3, Al3+. The sulfate radical, SO4, has a valency of 2, that is SO4 2-. Cross over the valencies. This means we need 2 aluminium ions and 3 sulfate ions to balance the charges. So the formula is Al2, open the bracket, SO4, close the bracket, 3. Brackets are used because there's more than one sulfate radical. Next is the carbonate of N. N here is potassium with a valency of 1, K+. The carbonate radical, CO3, has a valency of 2, CO3 2-. Cross over the valencies. So, 2 potassium atoms are required to balance 1 carbonate radical. The formula is K2CO3. Each carbonate ion combines with 2 potassium ions to form a neutral compound. Now, let's bring our periodic table to life. It's one thing to know where elements sit on the table, but it's another to watch them come alive in real chemical reactions. This next question will help you see how these elements actually combine to form compounds. Get ready. We're diving into the world of chemical equations, where atoms rearrange, bonds form, and new substances are born. In every chemical reaction, the number of atoms of each element must be equal on both sides of the equation. This is called the law of conservation of mass. Let's go through each part carefully. Reaction between K and V. K represents hydrogen, H2, a diatomic molecule. V represents oxygen, O2, also a diatomic molecule. When these two react, they form water, H2O. So the equation becomes as shown. 2 molecules of hydrogen react with 1 molecule of oxygen to produce 2 molecules of water. Always balance hydrogen first, then oxygen. Always place the correct state symbols. Next, the reaction between M and E. M represents sodium, a reactive metal. E represents chlorine, a diatomic non-metal gas. When sodium reacts with chlorine, it forms sodium chloride, a neutral ionic compound. The equation becomes as shown. Sodium donates 1 electron to chlorine, forming an ionic bond that produces table salt. Next, the reaction is between R and V. R represents aluminium. V represents oxygen, O2. When they react, they form aluminium oxide, Al2O3. The equation becomes as shown. Always remember to write correct formulae for reactants and products. Balance the equation so that the number of each type of atom is equal on both sides. Then put the correct state symbols. Now let's take things up a notch and explore one of the most exciting parts of the periodic table, the power struggle among metals. Which element gives away its electrons most easily? Which one dominates as the strongest reducing agent? Let's find out. Starting with Part A, identify the most reactive metal. From our grid, the most reactive metal is O, rubidium. As we move down a group, the atomic radius increases, meaning the outer electron is farther from the nucleus and is lost most easily. That's why rubidium, being the largest in its group, is the most reactive metal. Now for Part B, identify the most electropositive element. Again, our answer is O, rubidium. Electropositivity is simply the tendency of an element to lose an electron. Rubidium's outer electron is held very loosely. It practically jumps off. That makes it the most electropositive element since it has the largest atomic radius. And in part C, identify the strongest reducing agent. Once more, rubidium takes the lead. Because it loses electrons so easily, it readily donates them to other substances, reducing them while it gets oxidized itself. Here is the exam tip for you. If a question ever asks for the most reactive metal, most electropositive element, or strongest reducing agent, look for the group 1 element with the largest atomic radius. That's your winner. The element that loses its valence electron most easily. So in this case, O, rubidium, wears the crown in all 3 categories. Next question P. Let's now compare the reactivity of different metals based on their position in the periodic table. Comparing M and N. M is sodium, while N is potassium. Both M, which is sodium, and N, which is potassium, belong to group 1, the alkali metals. Reactivity in this group increases as we move down the group. Since potassium is below sodium, it has a larger atomic radius, meaning its outer electron is farther from the nucleus and is lost more easily. Therefore, N is more reactive than M. All right, comparing N and Q. Here, N, potassium, is in group 1, while Q, calcium, is in group 2. Group 1 metals are more reactive than group 2 metals because they only need to lose 1 electron to achieve stability, while group 2 metals must lose 2. Therefore, N is more reactive than Q, since N requires less ionization energy than Q to lose its valence electrons. Now, comparing M and Q. M, sodium, is a group 1 metal, and Q, calcium, is a group 2 metal. Again, group 1 metals are generally more reactive since they lose a single valence electron more easily than group 2 metals. Therefore, M is more reactive than Q. Here is a quick recap. Tip: reactivity of metals increases down a group. Group 1 metals are more reactive than group 2 metals. Question Q, A, asks, which element has the least ionization energy? Explain. Let's define the term ionization energy first. Ionization energy is the minimum amount of energy required to remove electron or electrons from the outermost energy level of an atom in its gaseous state. According to this grid, the element with the least ionization energy is O, rubidium. Why? Rubidium is a group 1 element, alkali metal, and is found lower down the group. As we move down the group, the atomic radius increases, meaning the outermost electron is further from the nucleus and shielded by more inner shells. This reduces the effective nuclear attraction on the outer electron, making it easier to remove. Therefore, O has the least ionization energy because its outermost electron is weakly held and can be removed with the smallest amount of energy. Part B of the question asks, compare the ionization energy of L and N. Now, L is lithium, while N is potassium. Both are group 1 metals, 1 valence electron. Ionization energy decreases down the group. Therefore, N has a lower ionization energy than L. Why? N, which is potassium, has a larger atomic radius. Hence, its outermost electron is further from the nucleus, so it is less strongly attracted and easier to remove. Lithium's outer electron is much closer to the nucleus and held more tightly, so it takes more energy to remove it. Next part, C of the question. Given first ionization energies, M and R are 577 kilojoules per mole and 494 kilojoules per mole at random. I. Write the first ionization equations and indicate their energies. The equations are as shown. The indicated first ionization energy for sodium is 494 kilojoules per mole, while that of aluminium is 577 kilojoules per mole, meaning aluminium has a higher first ionization energy. So, What is the explanation for this? Aluminium has a higher nuclear charge, more protons, and its valence electron experiences a greater effective nuclear attraction than the valence electron in sodium, hence more energy required to remove the first electron from aluminum than from sodium. Moreover, aluminium has a smaller atomic radius than that of sodium. Question R asks, identify the element with the highest ionization energy. Explain. The element with the highest ionization energy is Z, helium. The reason is, helium has the smallest atomic radius and a completely filled outermost energy level, making it electrically stable. Because of this stability and strong electrostatic attraction between its two electrons and the nucleus, a very large amount of energy is required to remove even one electron. Therefore, helium possesses the highest ionization energy among all the given elements. Next part of question R asks, compare the ionization energy of Z and C. Remember, both Z and C are noble gases and have stable electron configurations, but Z, which is helium, has a higher ionization energy than C, krypton. So, the explanation here is that helium is in period 1 and has a smaller atomic radius than C, meaning its electrons are closer to the nucleus and experience a stronger nuclear attraction. In contrast, C, though stable, is in a lower position on the periodic table, having more occupied energy levels that increase shielding and distance between the outermost electrons and the nucleus. Therefore, less energy is needed to remove an electron from krypton compared to helium, making helium's ionization energy higher. Question S is on the reactivity of nonmetals. Now, the most reactive nonmetal, the most electronegative element, and the strongest oxidizing agent is element W, which is fluorine. Fluorine is at the top of group 7, the halogens, meaning it has the smallest atomic radius, has the strongest attraction for electrons. This makes it the highly reactive nonmetal because it gains electrons most readily. It is the most electronegative since it attracts shared electrons more strongly than any other element. It is the strongest oxidizing agent because it easily oxidizes other substances by having the highest tendency to accept electrons. This is the tip. When identifying the most reactive nonmetal, most electronegative element, or strongest oxidizing agent in the periodic table, look for the group 7 element at the top of the group. It's always the most powerful in these properties. Question T says compare the reactivity of elements E and X. Element E, chlorine, is more reactive than element X, bromine. This is because reactivity among halogens, group 7 elements, decreases down the group. As we move from chlorine to bromine, the atomic radius increases, meaning the outer electrons are farther from the nucleus. The attraction for an extra electron becomes weaker. Therefore, chlorine gains electrons more readily than bromine, making it more reactive, more electronegative, and a stronger oxidizing agent than bromine. Question U. Select a pair of elements that react most explosively. The most explosive reactions occur between elements that are highly reactive metals and highly reactive nonmetals. In our case, the pair would be O, rubidium, from group 1, the alkali metals, and W, fluorine, from group 7, the halogens. Here's why this pair reacts so violently. Rubidium loses its single valence electron very easily because of its large atomic radius and low ionization energy. Fluorine, on the other hand, is extremely electronegative and readily gains an electron. When these two meet, the electron transfer happens instantly, releasing a huge amount of energy and forming rubidium fluoride in a highly exothermic reaction, one of the most explosive combinations on the periodic table. Question V. Identify the least reactive element. The least reactive element is Z, helium. Here's why. Helium belongs to group 8, the noble gases, which have complete outer electron shells. In helium's case, the energy level is perfectly filled with 2 electrons. Because of this stable electron configuration, helium has no tendency to gain, lose, or share electrons, making it chemically inert. It simply doesn't react. In summary, helium stands out as the least reactive element because it has already achieved the most stable arrangement possible in nature. Question W is about atomic radius trends. Part A asks, which element has the largest atomic radius? Explain. The element with the largest atomic radius is O, rubidium. As we move down a group in the periodic table, the number of electron shells increases. This makes the outermost electrons farther from the nucleus, reducing the nuclear attraction. Hence, rubidium, being the lowest in group 1, has the largest atomic radius among the listed elements since it has the highest number of occupied energy levels. Part B. Compare the atomic radius of P and Q. Q has a larger atomic radius than P since it has more occupied energy levels. Atomic radius increases down the group due to increase in the number of occupied energy levels. Part C. Compare the atomic radius of T and S. The atomic radius of T is smaller than that of S, since T has less number of occupied energy levels. Part D asks, compare the atomic radius of M and U. U has a smaller atomic radius than M. This is because U has more protons, hence greater positive nuclear force of attraction, which pulls electrons more firmly towards the nucleus, decreasing the atomic radius. Question X asks to compare the ionic and atomic radius of elements L and W. A. Element L, which is lithium, forms an ion by losing one electron from its outermost shell, forming a cation. The atomic radius of neutral lithium is larger than that of its ion. This is because, after losing one electron, the remaining electrons are closer to the nucleus, and the effective nuclear charge on each electron increases, pulling them in more tightly. Moreover, after losing its outermost valence electrons, it ends up losing the entire outermost energy level. Therefore, its ionic radius will have one energy level less. For element W, which is fluorine, forms an ion by gaining one electron into its outermost shell, forming an anion. The atomic radius of neutral fluorine is smaller than that of its ionic radius. This happens because adding an extra electron increases electron-electron repulsion and slightly reduces the effective nuclear attraction per electron. Question Y. Comparing the ionic radius of elements L and W. The ionic radius of L, which is lithium, is smaller than that of W, fluorine. When lithium loses one electron, it shrinks in size because the loss of an electron reduces electron-electron repulsion and allows the nucleus to pull the remaining electrons closer. Also, it loses an entire energy level. On the other hand, when fluorine gains an electron to form an ion, it expands in size due to increased electron-electron repulsion in its outermost shell. Question Z. Identify a metalloid from the above periodic table. The element identified as a metalloid is S, silicon. A metalloid is an element that shows properties of both metals and nonmetals. For example, silicon shines like a metal, metallic luster, but does not conduct electricity as efficiently as metals. It's a semiconductor. It can form covalent compounds like nonmetals, yet behaves metallically under certain conditions. In summary, silicon S is a metalloid because it bridges the two worlds, metallic and non-metallic, making it one of the most important elements in electronics and computer technology.
And there you have it. We've journeyed through the A to Z of the periodic table, unlocking mysteries behind groups, periods, ions, reactivity, atomic size, and even the metalloids. If you followed closely, congratulations. You've just built a rock-solid foundation in one of the most important concepts in chemistry. But remember, this is only part 1 of the mother of the periodic tables. In part 2, we'll dive even deeper, exploring patterns, anomalies, and real-world connections that will make you see chemistry not just as a subject, but as a story written by the elements themselves. So don't stop here. Like, share, and subscribe to stay tuned for the next thrilling chapter of the mother of the periodic tables. And as I always say, keep exploring, keep questioning, and keep the chemistry alive.